Hey everyone! Imagine popping a balloon. Boom! What really happens inside that balloon before it bursts? Well, gases are wild, full of fast moving molecules zipping around in all directions. These tiny particles barely notice each other unless they bump into something, like a wall or each other. That's why gases are the easiest to study. Their molecules are so far apart that their interactions are almost zero, except during those short, bouncy collisions. Even when gases seem still, they're buzzing with motion. We call this dynamic equilibrium. Nothing's resting, everything's moving, but on average, everything stays constant. And at low pressures and high temperatures, gases behave ideally, following a simple relationship P times V equals K times T, where P is pressure, V is volume, and T is absolute temperature. Simple, elegant, and surprisingly powerful. Now, what's this mysterious constant K in our equation? It's not just any number, it depends on how many molecules the gas has. So, we rewrite it as K equals N times kilobyte, where N is the number of molecules and kilobyte, called the Boltzmann constant, is 1.38 times 10 to the power minus 23 joules per Kelvin. That gives us the beautiful equation P times V equals N times Kb times T. It tells us that the pressure of a gas comes from the collective impact of billions of molecules colliding with the container walls. And guess what? If two gases have the same pressure, temperature, and volume, they contain exactly the same number of molecules. That's Avogadro's hypothesis coming alive. Let's meet Avogadro, the guy who connected the microscopic and macroscopic worlds. He said 1 mole of any gas has the same number of molecules, about 6.022 times 10 to the power 23. That's the Avogadro number. Now, with that, we define a universal constant, R equals NA times Kb, and our equation becomes P times V equals mu times R times T, where mu is the number of moles. For 1 mole of gas at standard temperature and pressure, that's 273 Kelvin and 1 atmosphere, the volume is 22.4 liters. And if we take the mass of the gas as m and its molar mass as m0, then nu equals m divided by m0. So, with one small equation, we connect the microscopic atoms to the macroscopic pressure, temperature, and volume. That's the real magic of physics. Alright, let's get real, literally. No gas is truly ideal. The equation P times V equals mu RT works perfectly only when gases behave nicely, that is, at low pressure and high temperature. At high pressure or low temperature, gases start misbehaving. Why? Because molecules start attracting or repelling each other, they get personal. We define an ideal gas as one that perfectly follows PV equals mu RT everywhere. But real gases? They deviate. There's even a density version of the equation, ρ equals P times m0 divided by R times T. So when you look at real PV curves, they line up with the ideal prediction only when the gas is chill, low pressure, high temperature. Lesson learned, gases are ideal only when they're not under stress. Sounds familiar, right? Let's bring back the classics, Boyle's law and Charles' law. When the temperature stays constant, PV equals constant, that's Boyle's law. Pressure goes up, volume goes down, they're inversely related. At constant pressure, volume is directly proportional to temperature, that's Charles' law. Heat a gas and it expands, cool it and it shrinks. Both of these are just special cases of the ideal gas equation. So the next time you heat a balloon and it grows larger, you're not seeing magic, you're watching Charles' law in action. Now let's mix things up, literally. What if we combine multiple gases like oxygen and nitrogen in air? Dalton answered that with his law of partial pressures, each gas contributes to the total pressure as if it were alone. So, P equals P1 plus P2 plus P3 and so on. Mathematically, P equals the sum of mu IRT divided by V for each gas I. That's why in a scuba tank, the pressure you feel isn't from one gas but from all the gases adding up together. In short, gases share space peacefully. Each one minds its own business but still contributes to the total pressure. Alright, let's solve one quickly. A vessel contains neon and oxygen with their pressure ratio as 3:2. According to the gas law, pressure ratio equals mole ratio, so mu divided by mu equals 3/2. That means the number of molecules also follows the same ratio, 3:2. Now, density depends on both mole number and molar mass. Since mu equals mass by molar mass, the density ratio ρ1 by ρ2 equals nu1m1 divided by nu2m. Substitute the values 3 into 20.2 over 2 into 32 gives roughly 0.95. So, the density of neon is slightly less than that of oxygen, yet they keep their pressure ratio perfectly balanced. Pretty neat, right? Dalton would have absolutely loved this one. So, to wrap it up, gases might look simple, but they're full of life and motion. Their behavior, pressure, volume, temperature all come down to how fast and freely molecules move. The ideal gas equation, PV equals NKBT or mu RT, is the golden bridge between microscopic motion and macroscopic measurements. From Boyer's law to Dalton's law, every gas law emerges from this single elegant principle. And though real gases may not be perfectly ideal, the model helps us understand everything, from weather balloons to car engines and even the air you breathe. I hope you now see gases not as empty space, but as a buzzing, invisible crowd of molecules, always moving, always fascinating. See you in the next class. We'll dive deeper into how this motion defines pressure and energy. Until then, stay curious and keep that scientific spark alive.